One of these days I'll remember to bring a bar of soap or something in. But it's actually getting worse, you know.
Are you going to post the lectures right now?
It'll take an hour and a half for WebEx to, to convert it to MP4, and then I'll upload it.
Because I want to see the problem you went over.
At the beginning? Yeah, it'll be after this class, and I'll do it. It takes it about 1.5 times the duration of the class to build the MP4 file, because they're doing it between other more important stuff, I guess. I don't know. It's slow. It's like they're doing it on my laptop. Maybe that's why my laptop's so slow. They've hijacked my laptop. So it'll be up a little later this evening.
Okay.
See you later. Hello, guys. I feel like I should have like a Vincent Price voice or something. You know? Okay, we made it all the way through.
Yeah.
This. Does this look familiar? Yes. No, WebEx didn't ever make it. I don't know. I don't understand why. Well, just listen to the Thursday morning one. You'll need the Thursday morning one anyway to understand one of the homework problems, because I did not decide I was going to include it until after our lecture. I can go over it more now for you guys, but I doubt it's going to work because unfortunately you notice I have no stickers? Yes, it finally died. I pronounced it dead on Friday evening at about 8:48 p.m. We had a little service and we buried it in the backyard. And I pulled out one of the other two that I had stored up for Armageddon, and immediately started the process of moving the hard drive over, which of course didn't work because the ROM was different. And then I solved all that, moved everything around and stuff, and then tried to install a newer operating system. Of course, that wouldn't work because the machine's too old, so I had to hack the OS and do a Franken-Mac kind of thing. And now Office will not authenticate, so I can't write anything with Word or PowerPoint or Excel. So they're going to just force me to use Google's products. Anyway, it's a living, right? So let's see. We started with this. Let me see if I can get past this to where we were. We talked about this already. I think we talked about all of this junk. And we finished chapter 2, if I believe. Okay. So let me fix a couple of things on this settings, and then we'll get going. So some of the stuff doesn't work right on my laptop, and I apologize for that. But I did try to get everything in here installed. The one thing I missed, and I thought about it in the car on the way over, was the drivers. I don't really care about that. I just want to install it. Go away. Where are the drivers? Let me see if I can just do this really quickly. This is either going to go great or it'll be the end of the lecture. So you can hope for whichever one you want, depending on how much you like it. Yeah. So let's see if this will install it, because we need, in this class, we need the tablet. It's very true. Just hope it doesn't make me reboot, because I'm not going to do that. I bet it will, though. In fact, I'm almost positive it's going to do that. Yeah, but it takes down the WebEx. Yeah, okay. I get it. Irony. Yes, my irony flag was not set, so I didn't quite get that. There's zero chance this is going to turn out well for me. But I already have regrets, so I haven't even finished with it yet. I'm not going to repeat that, but yes, it's exactly like it. As someone over the age of 30, so who ought to know. Yeah. Okay. Let's finish this up. It was quite miraculous that I got almost everything done. Let's see. Dropbox only has 5,000 files left. Wow, that's down from like 260 something thousand files it had to pull back down. to sync. But I don't put anything on the laptop. It all lives in Dropbox, so if the laptop dies, I just move on with my life. All right, well, this thing is going to finish doing whatever it's going to do. Oh my God, it works. I can't believe it. All the bad stuff I said. I'm so sorry. I take it back. Okay, now go away. Yay! Yeah. Well, we'll let it finish. In the meantime, we are going to go ahead and begin with our lecture. So I needed to do that between lectures, but I got a ton of questions, so I apologize for that. Okay, chapter 3. Let's see if we can get this thing open. Okay, we've talked about a little bit of this stuff. Oh, God. Yeah, that's just going to stick with PDF. We're down to delay, loss, and throughput. And so what no, this is not right. Hold on. We've already been over delay, loss, and throughput, like, until we're sick of it. We don't need to do that again. Here we go. This looks more like it. Bingo. Let's try this one. How about, here we go. Transport layer services. So far, we've spent the whole lecture, other than the intro chapter where we went kind of through everything soup to nuts. The chapter we just finished, chapter 2, was all application layer. So email and web servers and HTML files and FTPing and BitTorrent and DNS, all application layer protocols, all application layer programs. When in doubt, if asked, what layer something runs at, unless you know for a fact it's at a different layer, and you can just like answer it like that, your gut answer should always be application. Just always guess application will be right 99.99% of the time. Almost everything that uses the internet sits on top of the same 4 layers underneath that have been there for a long time, all the developments at the top. So all the hundreds of thousands of apps that we've written, they're all up at the top layer. So we need to understand what's going on under the hood, because as programmers, we don't often get to look at that. We spend most of our time up at the top. Parece que tiene dos versiones abiertas. Okay, I don't care. No, I'm not going to buy it right now. All right, so we want to understand what's going on the layer below. So the layer below application is transport. Remember, please do not take advice. Physical data link network, take is T for transport. Advice was A for application. So we're at the second layer from the top, if you don't count the other 3, money, politics, and religion, on top of everything else. So we're going to learn about things like multiplexing, demultiplexing, how to make this internet look more reliable to a programmer, and how to deal with 2 very different types of the speed at which you send stuff. One's flow control and one's congestion control. So sneak peek flow control is something you negotiate with the other end. If I send you a truck with 10,000 pounds of sugar, do you have a place to put all of it? That's flow control. Congestion control is, it's going to take me another hour to get there because I ran into traffic. That's congestion control. Is there another route I should take? Well, ask Waze, for example. And we'll learn about the 2 big ones that are out there. There is a third one, stream control transport protocol, which is used for video streaming. And it's a very valuable tool that will help coordinate between 2 ends and switching speeds and compression and choosing between manifests. But we'll spend our time in this class looking at UDP and TCP. So we'll start off by taking a look at the services that they provide. So there are 2 different transport layer protocols that are popularly used. One's UDP, one's TCP. They're different, so why do we have 2? What do they do that's different than each other? And then we'll poke a little further on through. But let's just at least start with that. So what a transport layer communication does is provide a logical stream of communication between 2 hosts. Remember, everything that hangs off the edge of the network is a host. Everything in the middle, for the most part, are routers. This has nothing to do with communicating between routers. You can see logical end to end, right? So this is talking about one host to another. Your laptop to Amazon.com, for example. Right? So how does that happen? So you have an end-to-end protocol running also inside your program, probably, like HTTP, for example. But the same thing is going on a layer down below. There's software that's running as part of the operating system that's got the task of trying to get your data from one end to the other so that your program hands its message to this thing and it takes it from there. And the next place there's another module of software running that knows how to interpret what this one did is all the way at the other end of the connection at the other host. There's nothing in the middle that has any idea what a transport layer is or what it needs to do with your stuff, or we'll get to that later. So this is sort of end to end. So this would be like taking a letter, a birthday card, writing it, sticking it in an envelope, and dropping it in the department office outgoing mailbox. And that person has a computer science peer in the other campus, Clear Lake, let's say. And so they get it to them. They make sure it arrives, they check, they figure out how to do it. All the other details of like what color is the mail truck and what time do they come by and how many mailboxes does it go through and does it go straight there? Does it have to go downtown first? They don't care about any of that stuff. And similarly, those people who are doing that couldn't care less that it's a birthday card. It doesn't mean anything whatsoever to them. They don't care that you know the person in Clear Lake. Doesn't make any difference whether you know them or not. I'm still delivering it just the same. And so there's some separation going on. All right, so what programs will do is break things into messages. And then what the transport layer will do is potentially resize those things into smaller chunks so that they won't overwhelm the network. Because you need to share this network with lots of users, and one way to be a good citizen is to not try to drive onto the on-ramp of I-45 with a vehicle that's 400 feet long. You're just going to be a complete pain in the butt for everybody else, if you can even make the curves. So don't do that. Just break it into smaller things, send the school on several different buses. Don't try to put them all in one giant one. Okay, so you know what the A380 is? Big old airplane. Largest commercial production airplane was made by Airbus, and they announced it, I don't know, 10 years ago, and they've stopped production. They're going to stop production. They canceled it. It was an enormously big mistake. Billions of dollars. And Boeing stopped theirs before they ever even did it. And they went instead with the Dreamliner model, which was 2-engine. And so this one had 4, so it's the end of the 4-engine big commercial airplane, we think. So it's interesting, you can still see different ways of moving people around as well. Think of that as something like the transport layer. All right, so we'll talk a little bit more about this. Okay, below the transport layer is IP.
Professor Long, yes. I don't mean to interrupt. You haven't shared your screen.
Oh, thank you very much. Fortunately, it's just like been one slide so far. Thank you. Appreciate it. You should interrupt 100% of the time. So I'm really glad you did that. I'm grateful. And now I know what I'm going to see if I open chat. It's like, no, 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 no. There's no video, blah, 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 blah. Yeah. So thank you. So that's what you guys should do. And if you see the messages coming across at the top, they're so high they get cut off. Do one of these or throw something. Sometimes it's so bad, I'm like so in the zone, you're just going to have to like, stop, turn your screen sharing on, or walk up and turn this, hopefully never that bad. But, okay, so there's a layer below, which is the network layer, which is IP. We'll talk more about that. That does run in all the routers. But this is really logical communication, more or less between the processes. So whatever program you're writing, let's say your web browser, to talk to the web server, there's a transport layer companion that's going to guide your packets through this journey all the way from one end to the next. So the household analogy the book uses is a bunch of kids in Anne's house. These are different processes running in the same computer, and they're all going to be sending letters to the 12 kids in Bill's house, 12 processes running on a different computer. So the hosts are the houses. The 12 kids are each a different program, a process, and the messages that they create are the letters that they put in envelopes. And so what the transport protocol is really trying to do is gather all the letters from Anne's house, get them all the way to the other end, and hand them back out at Bill's house. But they don't really care much more about that. So Anne's job stops when she puts all these things in a big envelope and hands it down to the mailman. And Bill's job begins when the mailman or the letter carrier hands it back up and they have to redistribute them back out. So this program is doing that all the time with all the packets that are coming in and leaving your machine. All right, to make sure they get to and from the right the right program. Okay, so the two protocols again are TCP, which is a reliable transport protocol, transport control protocol, and then UDP, which is unreliable. TCP's evil, lazy twin brother. He's got a bad attitude about everything. So they say no frills. No, he's a lot more dangerous than that. Neither one of these things provide any promise, because they have no way to do it, of how long it's going to take your packet to arrive at the other. How long it's going to take your packet to arrive at the other end. I'm glad that didn't come off. They also have no control over bandwidth, so they can't guarantee that you're going to be able to send so many packets a second. They don't have any control over any of that. What they do have control over is whether or not they choose to keep really close records and keep track of whether they've heard that the packet made it to the other end or not, and keeping a copy of it in case they have to resend it for you, so you don't have to be bothered with any of that stuff. They can figure that stuff out. This is the way Amazon should work. So they already know that your package didn't arrive and resend it for you without you having to call and bug them about it. Why should you have to do that? They already have all of the data. So it'd be something like that. Okay, first thing we got to figure out is what's multiplexing and demultiplexing. So multiplexing is when you take a bunch of different pieces of data that all need to share a transmission circuit, like a network cable, and get them all in order, some sort of order, and out the door and on the wire. So one of the things you've got to figure out is who goes first and who goes second. You have problems of what if one person is sending so much stuff, they're kind of drowning everybody else out. How do you want to deal with that? Do you want to round robin, or do you have priority queues? Is it like one for you, two for me, or how exactly, what's the rule? So this happens pervasively throughout devices in the interior of the internet, a layer down below, but it also happens up here at the multiplexing layer. So at any given moment, you may have 20 different programs that are trying to send packets out of the computer. They're all calling the transport layer software in the operating system, and then that software has to figure out how to keep all that stuff in order and then hand it down one at a time to the layer below. At the same time, it's trying to grab stuff that's coming in and hand it back out to whoever it needs to go to. So what we see in this example is two applications, P3, Process 3, and Process 4, that run on two different hosts, and they have companion modules, one for each, that's running inside this server in the center of the diagram. So P3 can send stuff, it looks like here, to P1, and P1 can send stuff back. And if I follow these errors correctly, P4 talks to P2. Well, that makes sense, right? So you can have email program talking to an email server and a web browser talking to a web server. You could have those running on the same computer, right? The problem here is what's really going to happen is you're going to have like 300 of these all running the browsers, all trying to talk to exactly one application in the middle. So that's going to be a lot more complicated than this diagram suggests, because this diagram seems to suggest every time you have somebody who wants to talk to you, you spawn off another copy of your program, and you're just not going to do that. You're not going to run 500 copies of your web server on your server. It's extraordinarily inefficient. It can't handle it. So we'll take a peek. We'll talk a little bit about it, and I'll give you a hint at some techniques that we use as programmers to overcome this problem. It's a big issue, and we're really good at solving it. So this is not one that's like killing us. We know how to do this, as evidenced by the fact that you are able to browse the web, even to popular sites. So what these things basically do is multiplex stuff as it goes out to share the same outbound connection, and demultiplex it as it comes in to separate them and give them back out. All right, so how does the system know how to multiplex? There are 4 numbers that are key. We'll start by talking about the first 2 of them. Every time you start up a program that is a network application, that means it knows how to use the socket library to request connections. And it will be assigned a port number by the operating system. It is exactly like walking down to the port at the water's edge for a big busy Baltimore, for example, and they assign you a port number and say, okay, if you want to start sending things across the ocean to someone, here's your port. Now, it's going to be loaned to you temporarily because who are you, after all? So you can show up, and I'll let you use this port number. Your port number is 16,283. It's a lot of ports, a big port. And when you're done, I'm going to take it away, and I may give it to somebody else later. Now, if you're really well known, you know, if you're like Princess Cruise Lines, you have port number 80. That's your port number, always. So if people come in and it's a Princess boat, I just assume I'm going to direct it to port number 80. So that number you don't get to use because that's reserved for somebody else. So you're assigned these things kind of randomly on the fly, and that number stays with your message. When it leaves, it says, I'm sending you this from this computer and port number 1000. So if you have anything to send back to me in response to my question, make sure you address it to apartment or port 1000. So that when it gets back, the port master knows, you know, which person to send it to. Because everything comes in over the same water. The next layer down will have IP addresses, which you guys kind of know what those things are. That's a number that's given to your whole computer. So if you tell me the city and the port number, or the airport and the gate number, or et cetera, I can point to a specific resource, but I got to know both. It doesn't help to say, I'm arriving at some airport in the world at gate 6. Well, like, where exactly? Well, I'm arriving, take it back, I'm arriving at Houston. Okay, what gate number? So you got to have both. So I like to use a little template to kind of draw this out. Do not panic, that is not the template. Okay, so the template I like to use is a square. And you can draw it a variety of different ways. You can assign these things to either columns or rows. It makes them no different. But one of them is going to be IP addresses, and the other one's going to be port numbers. So this will be the source and the destination. So all of your packets are coming from one computer going to another on the internet. And furthermore, they're coming from a certain port number and going to a certain port number, right? So all 4 of these numbers are on every single piece of data flying around the internet. And these 4 pieces of data are enough to say exactly from whom and to whom is this data flowing. Every packet goes from one application to one application. You don't have them like going to everybody. It's one-to-one. There'll be some exceptions we talk about later. So for example, if I am sending a bunch of packets to the New York Times website, then I may be coming from port number 16,000 and going to port 80. And I may be going, I'm not writing this exactly the way, and you know, I may have 128.249.27. whatever, and then I have another. So another way of writing this thing is basically to say, let me think of a better way of doing this. Another way of writing this that might make more sense. There's a ton of different ways of trying to map this stuff out. This one I think I like better. Port and IP, they each get a row. So now you can tell me your source and destination port number and your source and destination IP address. So if I see 2 packets on the internet and all 4 of these things are equal to each other, what does that tell me? Well, they're part of the same communication stream. They're probably like back-to-back packets, maybe sending an email message from one person to their server, or maybe it's back-to-back packets. Maybe there's a million of them, if I keep looking, that are handing the contents of a web page to someone's browser. So there's a flow of communication. Where it gets interesting is if things are different. So these port numbers are randomly assigned, generally, if on the sender side. You and I are not well known enough to be assigned permanent port numbers. So just because I see 2 packets on the internet that have the same source port number doesn't mean they're coming from the same person. In order for us to make that conclusion, they have to be coming from the same IP address as well. So you and I both could randomly be assigned the same source port number. We both leave in our little boats from port number 1000. But you leave from Cyprus and I leave from Athens. It's not the same. So you need to look at all 4 of these things. So back to the lecture, what we're going to look at in this chapter at transport layer is what these port numbers look like, how big and small they can be, what the ranges are, and then how do we organize them. It's very common when you're drawing internet protocol diagrams and showing people data structures that you draw things like this, 32 bits wide, 4 bytes wide. That's just tradition. Of course, it goes on the wire as a string of bits in a row. But to keep things sane, we draw it. In fact, we'll even design protocols so that we'll make fields bigger maybe than we needed to so that it fits this 4-byte boundary rule, unspoken kind of rule, to make things a little easier to diagnose and understand what's going on. So that's what the segment looks like. So if you don't have a connection with someone, then you basically are randomly sending packets. They never know what to expect. They handle the one that comes in, and they move on to the next. So this would be like individual customers showing up at McDonald's at the Student Center, just one after the other. They don't really know that there's any relationship between the students or they're all part of the same group or whatever, unless you tell them, look, all of these guys in blue shirts, those ladies and gentlemen, they're all part of the group. I will pay for them at the end. Just take all their orders. Now they have different expectation. There's like this communication going on. All right, so sockets will be used to create a local port number. So in this case, I have a new datagram socket, and I was given socket number 12534 randomly by the operating system by this code. And when you want to send something into UDP specifically, you have to specify every single packet has to have the IP address and port number because they have nothing to do with each other. In other words, one packet after the other, and nobody notices they're all wearing blue shirts or whatever. It's just like another customer. Like, where are you trying to get to? Okay, what would you like? Okay. And they don't see any stream. So that's very lightweight, but can be very inefficient because I don't need to really send the IP address and port number every time, do I really? If I'm sending a whole string of packets, isn't there like a better way to design that? So when the host receives that segment, it checks the destination port number, which is also in there as we saw, and it will send it to the software instantiation of a socket, which was created when the server started up that morning, made a socket call, and asked to be bound to the incoming port number, basically saying, I will handle anything that comes in on port 80. Thank you very much. Anything that comes in on port 80, I'm here, I'm running, I'm waiting. Please take it off the network and hand it to me. So servers start up in the morning and they wait. They wait for data to show up. So that's what is happening at the receive side. So the datagrams that come in with the same destination port number but different source IP addresses are coming from different computers. So you need to keep track of those things. If they're coming in with the things that are the same, then you send them to the same place. So here's kind of the first dilemma. You can have things arriving in from all over the internet, and they're all trying to get to the same program. How am I going to keep track of them? You have to set up a data structure, a series of buffers, and just track them one by one. You have to keep track of it. All right, we'll talk a little bit more about that as we get further into this. So this is what connectionless looks like. I open up a socket. The other person does as well. We're given, fortunately, mercifully, different port numbers. And the server is listening in the middle. He starts up in the morning. And these guys don't start up until somebody opens up a network application like a web browser, and they cause something to happen that needs for data to leave your computer. Open up the browser. If you have a home page by default, that's all it takes. Open up the browser, presto, it sends out a request for the home page. I don't have mine set to do anything. It just shows me basically a blank screen. I have to type in a URL and hit return, and then my browser has something to do. Once that happens, then I am going to have a socket. So maybe my browser opens up a socket when it first starts up. Maybe it waits until I actually send something. Most of the time it'll be the former of the two. It will try to look for a network connection, but it's not going to send anything until you give it something that needs to send. So it'll wait. The server, on the other hand, is constantly listening and waiting. So how is this thing gonna work? So I'm going to send a packet out with this source and destination combination. Anything he sends back, you reverse them. So now what was the destination becomes the source. and vice versa with the other side. Same thing's going on at the other end of this connection with the other device. So in this case, if I'm sending something from P4 to P1, then the source port number is going to be 5775, and the destination port number is going to be 6428, which is interesting because it's the same destination port number over here. Well, it's the same program. Why wouldn't it be? And then when P1 sends something back, the way the network knows not to send it to the left, but to send it to the right is in part because the port numbers at the destination are different. So now the source port number is 6428. Well, that's the same as this guy, but the destination port number is different. So before it leaves my computer, it will use the fact that the destination port number is different to associate it with a different IP address and send it out the door. Okay, so a socket is identified by those 4 items that I mentioned, and a demuxer will use all 4 values to figure out who to direct things to. And if your code is written in a way to support lots of different TCP sockets at a time, if your server will handle it, then every single one of those, and most servers do, every single one of those will have its own 4 combination of numbers of source, destination, IP, and port number. Do email service well, email runs on top of TCP, not UDP, but yes, it runs exactly like this. Every application layer protocol you ever build uses all 4 of those pieces of information. The only difference is whether they have to put it on every single packet, or if they can request a higher grade of service where you don't have to do it every time the system remembers who you are. And that's one of the differences between TCP and UDP. So web servers have different sockets for each connecting client. So when somebody comes in, you will spawn off another socket and assign that user until you don't have any more capacity left. And then you stop taking them in. So how do you write your code so that 2 people are wandering around and they're setting variable values and running snippets to grab pages? Well, there's a couple of ways of doing it. You can have multi-threaded code or reentrant programming. There's other techniques, but basically it's a way of parallelizing blocks of your code without having to run multiple copies of it, without having to have full-blown multiple copies. And we have to be good at that because we don't have enough resources to do it. So in this case, I have now 2 programs over on the right-hand computer. P2 and P3 are the 2 processes running on there. They are given different source port numbers, 5775 and 9157. And they are both trying to go to the same destination. IP address is B. They don't want to put a whole number here, so just use letters B. And they're both trying to get to port 80. Well, this guy's also trying to get to port 80 over here. He's coming from computer A, and he's been assigned port number 9157. Wow, that's a coincidence. So both the application P3 and this one over here, they were both assigned port number 9157. So if that's all I'm going to try to use to keep them apart, it's not enough. I'm going to have to use the IP address as well. So this is 9157 on computer A. This is 9157 on computer C. All right, so in the middle, I've got some way of accommodating all 3 of these users at the same time by having software sockets that are built. And they're all 3 demuxed. As these packets come in, they're handed to different sockets, and this server is threaded, so there's only 1 copy of the server at the top. So there's you may learn how to write multi-threaded code in your operating system class, for example. All right, questions on this? So far, so good? Makes sense? Have you seen this stuff before? Have you guys heard of multi-threaded servers or threaded code? Some? Okay, have you written it before? Yeah, well, sort of. Yeah, okay. Are you taking it here? Okay. What class is it? Oh, well, it is operating system then. Okay, well, that's kind of the classic one. Okay, so far, so good. So what are the 4 values that uniquely identify the sockets in the packet? Source and destination, what? IP, and yep, you got it. IP and port. Good. All right, so let me ask you a couple other questions. I see 2 packets on the network next to each other. one here and one here. Port and IP. I'm running an OS that's not really supported by this hardware, so it's like slow. Okay, let's say the source port numbers are the same. In fact, I'm going to do this a little differently. We're going to change to a different color. The source port numbers are the same, and the destination port numbers are the same. Does that mean these two packets are coming from the same computer? Does it mean they're going to the same computer? Does it mean they might be doing the same type of thing? Based on what? Okay, so because a process is given a particular port and they'll use it, so is it because both of these things are equal, or was there one of these in particular, like the fact that these were equal between the two or these were equal between the two? What made you think that maybe they're doing the same thing? You're correct, by the way. The destination port is right. So for example, if wherever these are coming from or going to, if they're both trying to get to port 80, we know they're both going to web servers, right? So they're both probably doing the same things. If they're not going to a well-known port, a low-numbered port number, then all bets are off with that. You know, if it's like you are writing some test code between two systems, you're not supposed to use a low port number. Nobody's going to catch you if you do, but you're supposed to use high numbers, in which case it would just be kind of a crazy coincidence. Most popular applications have been assigned and continue to be assigned low port numbers, so-called well-known port numbers. Okay, what if I add to this the fact that the destination port number, I wrote that wrong. That's what I drew before, was destination port number. Okay, so let me, you guys answered the right question even though I didn't draw it quite right, which was this situation. Yeah, it's mysticism is right. All right, so suppose now I tell you the destination IP address is the same. What else can you tell me that these things have in common, these two packets? So let's continue with your example. Was it like a web browser going to a web server maybe, like port 80? Okay, so now what can you make that statement stronger now that I've showed you these two things are the same? Yep, going to the same host, going to the same computer, probably the same website would be a decent bet. Not guaranteed. It could be going to a big server at GoDaddy that hosts 100,000 websites for little startup, do-it-yourself web pages. But you know, generally speaking, it's going to be it's going to be the same. Now, they may all be offered the same IP address, and therefore they may all really run on the same copy of web server code. Yes. Uh-huh. By HTTP, we'll have the URL they're looking for and the name of the host, or the name of the domain. And so they'll go, you know what, all these domains you can get to by asking the same web server. But in the GET message, where you ask me exactly for the file, don't just tell me like index.html. That's not enough. You're going to have to tell me the domain name you're trying to get to, like, you know, textprof.com, and then the page that you're trying to get to. You're going to have to tell me both of those things. So it's a third layer of multiplexing that goes on. Does it all go to the same server in Arizona? Check. Does it all go to the same program running on that server, my Apache web server? Check. Yes, they do. Then I have 250,000 customers, one-page websites here. How do I know which one to give you? Well, this won't help you. You're going to have to tell me even more detail inside the protocol. Same thing with email. I can have one server set up to receive incoming email SMTP messages for 100,000 domains. It's all the same one copy of Outlook server. So how does Outlook server know what to do with it? Well, look inside the SMTP and it will tell you the address, somebody at textprof.com, for example. Okay, that's the mailbox I need to put it into. All right, so there's addressing. You'll find things that you do to keep this sorted out at every single layer. So we're all going to leave here and we're going to drive, let's say, on I-45. Is that enough to distinguish us apart from each other? No. What else do we need to know? Well, you need to know the license plate number on the car. Okay, that narrows it down, right? Is that enough to distinguish us from each other? Well, not exactly. You need to know, like, where are you trying to go to, or to maybe look at a different type of question, what your driver's license is. Different people can drive the car. So there's different layers of addressing and all kinds of schemes that we use. All right, so we've decided so far it's going to the same computer, the same program, the same socket, from two possibly different computers that by coincidence have the same port number. The last thing is if I tell you these two are equal, now you can tell me, okay, these are two packets in a row coming from the same program going to the same program. So you must have opened Wireshark and grabbed, like, 5 packets going to my website or something like that. Okay, so being able to think through the logic of that with different combinations is important. Okay, so this is lecture 9, I think. Yeah. So we've got time to go through lecture 10. Okay. I think these slides are all out on your class server, class folder. Is that right? Okay, thank you. Now, if I've ever overrun the runway and am doing stuff that's not out there yet, please stop me and I'll just drag it over right there. Okay, to continue on with connectionless. Whoops, a little too fast here. Let's go in a little bit of specific detail around UDP. So UDP was defined early on. It's an old 1980, 1979 RFC, maybe even earlier than that. I'm sure John Postel wrote it because his name is on most of the early RFCs because he was kind of the group scribe for everybody. John Postel, 1980. Nailed it. Okay, so I've only looked at it 100,000 times. It's not impressive even to me. So here they basically show you the source and destination port number. You'll notice it's 31 bits. Like I mentioned, they all show everything 4 bytes wide, and they kind of go through it. So data octets are combinations of 8 bytes of data at a time. Okay, why would you do things? I told you this was all done in 4-byte chunks, right? And right here, right off the bat, I mean, the very first page of the first one I open, and they're telling you that they're sending things in 8-byte chunks. That's what an octet is. So why would you send things in 8-byte chunks if it's customary that you draw this thing 4 bytes wide? Why not just draw it 8 bytes wide then? Well, it has to do with how you allocate bits. And if you don't have enough bits to tell somebody, well, first of all, you don't need enough bits to tell somebody exactly how big this packet is in bytes, because that's pointless. It's always going to be a multiple of 4. We've talked about that. So just tell me how many quartets it is long. That's good enough. How many 4-byte chunks is this packet? And save those other bits for something else. So whatever I find in the length field in this case, I would multiply it by 4, and that will tell me how many bytes to continue to read this data before I say I'm at the end. But what if I want my packets to be bigger than what I can represent in 16 bits here times 4? Now, that's not very big. That's only 64 bytes. That's a puny little packet. What if I wanted it to be, twice that big? 128 of these chunks. So maybe what I'll do is decide we're just going to let this length arbitrarily represent how many octets instead. So what that means is if you, if your packet ended at like 31 bytes, you're going to have to pad it to get it to 32, so it's a multiple of 4. Well, now what it means is you're going to have to pad it to get it to a multiple of 8. You'll find we do this constantly. You'll see lots of examples of this, and I'll continue to reinforce what that means. So UDP is no frills, bare bones, the evil, lazy twin brother of TCP, and it's sort of best efforts, which basically means couldn't care less. So you give it a packet, it'll just throw it on to IP. So if you guys are like baseball aficionados, then there's some really funny classic scenes where the pitcher was kind of ticked off at the umpire, and when they request it, the umpire will give them a new ball, but within reason. You know, it's like scuffed up, or they don't like it, and the balls are all kind of scuffed up before the game anyway by the referees or by other guys. They smear a certain kind of mud on it. But you know, if the guy's in a bad mood, then you end up with this classic scene of where the ball goes out to the pitcher looks at it, doesn't like it, he throws it back. Umpire throws another one out, pitcher looks at it. You know, it's obvious he's in a crappy mood because he doesn't like the calls he's getting. He throws it back, and so the umpire throws him 2 balls. You're never supposed to have 3 balls in a baseball field. So it's kind of funny. You can have some things like that. So that's kind of the attitude UDP has. You hand it a packet, it just throws it out. It doesn't bother to check to see if the host exists, or it's turned on, or there's a program listening on that socket number, or if your packet makes it, or if it's more than they can handle, or if it congests the network and causes routers to fall over dead. It couldn't care less. It just dumps the traffic as fast as you can get it onto the wire. It has more important things to do. So this is suitable for applications where you don't need a high degree of hand-holding and where time is of the essence. You don't want to delay the packet at all and get it out the door. It's also appropriate where it's a type of protocol where if for whatever reason the packet doesn't make it to the destination in a reasonable amount of time, you don't really need to do anything because the user will gripe about it and do it again themselves. For example, if the web page doesn't come back within half a second, you start hitting reload. You'll do that on your own. The protocol doesn't need to do that for you. We're impatient enough. Same thing with DNS. If you don't get a DNS relay, just try reloading and do it again. So that's one class of where, then what's the point of me like adding all this on if you're just going to do it again? The other reason for doing it is if overhead delays it. Like, can you think of some applications where maybe you don't care, some that you've actually used where you don't care if all the packets get there, you just need the ones that can get there to get there as quickly as possible. And you're okay if some of them get thrown out. Video streaming, every video streaming app you've used, if it's live streaming, you may not tolerate it if it's a pre-recorded program. You may insist that they buffer enough and delay things enough to get missing packets resent to fill in the holes, like Netflix, for example. But if you're watching DirecTV, maybe that's okay. What's another example that's not so bandwidth intensive as video? Audio, radio streaming. Audio streaming, you can drop lots of audio packets. There's no point if you figure out you're missing packet 200 to go back and resend it again. It won't make any sense. It'll play a sound that doesn't fit anymore, right? You know, it's like 10 milliseconds, 50 milliseconds, something short like that. There's also other things like status messages. There's a bunch of very important protocols that use UDP, like DNS uses UDP, for example, because not so much because of speed, but because there's just no point in doing it. It's also easier to kind of see what's going on. But so therefore it is called connectionless, and it will not do anything to see if packets arrive in order. The drawback is that every single packet UDP sends has to have a complete return address and destination address. It has to have all 4 pieces of that information we talked about in every single packet. Because it has no idea how many there are and all that. So for this reason, some network managers prohibit any incoming UDP traffic from the internet that hasn't been initiated by a connection that started from inside the network. So if you open an app and go to radio.com and ask for the baseball game to stream down to you, they will let those UDP packets in because they're associated with an outgoing connection they saw first. So they will observe the IP address and port numbers as they leave, and they will let the reverse back in. But they will not let any other UDP packets in. They'll just stop them at the farthest edge they can because they're denial of service vectors. You can flood tons of UDP traffic at somebody and just completely overwhelm them. So you make sure you have a router fast enough to drop all of those. A typical enterprise, 50% of the traffic coming in that's being delivered to them by the ISP is crap. It's traffic they will never let into their network. Half of all bandwidth. So I'm like, why can't you stop that on your network? Why do you have to send that to me? It's hard, but there's stuff that we're learning to do that better. AT&T is, for example, had built heuristics to say, you know, I can see there's this attack going on. I'm going to teach my devices at the edge of my network where this massive traffic is exchanged with other Tier 1 backbone providers, and I'm going to drop it all there instead of ever letting it in. Right? So you can do things like that. So no handshaking is ever given. Each UDP segment is handled totally independently of the others, and you use it for some of the things that we talked about. If you want to make your thing reliable, if you care that the packets all get there and you insist on using UDP, then do it yourself. Write it into your application. If you want encryption to protect the contents of your packets on top of UDP, great. Add the encryption in your own code. Figure out some encryption thing you're going to use with the other side on that. So that's a little bit about how it starts. The length is in octets. We talked about it. So why do we have this thing? Because it's very, very fast to get stuff out. The connection adds a round trip time. It adds delay. It's very, very simple. There's no need for state to be kept at either end. Very small header. That's it. And it can blast away as quickly as desired. So if you got stuff you want to try to get out as quickly as you can, UDP is your choice because it's not going to bother checking. It'll just take your orders and like drop it out. So UDP does care if the packets arrive corrupted or not. So there is a checksum. Do you guys know what checksums are? Some of you do, some of you don't. Is that true? Okay. So a checksum is a number that you calculate that is based on passing the contents that you wish to protect through some formula, and it cranks out a number. It could be, for example, multiplying all the numbers together and just taking the low 8 bits. That's it, just the low 8 bits, and then tacking that onto the data that you send. So it's possible that other numbers, other strings of numbers when multiplied together will give you that same low 8 bits, but not every possible permutation will do that. Most numbers, if you change the bits in your packet, 1 or 2 or 3 bits, you're probably not going to get the same kind of low 8 bits when you multiply. Or you take the whole thing and treat it as one giant number and divide it by some big number and see what the remainder is. And then send the remainder along with the packet. And at the other receiving end, whatever it is they get, they want to know if it's corrupted or not, so they're going to try to reproduce what you did. They'll take the packet, divide it by that big number. You guys have agreed in that in your code ahead of time, and they'll look at the remainder you sent and see if they match. If the remainders do not match, they throw the packet away. It doesn't matter if what got corrupted was something in the packet or if the remainder itself got corrupted. Either way, the packet's now corrupted, and you throw it away. Make sense? So that's an example of a checksum. Really simple example of a checksum is just parity. Have you guys used parity before? Parity is like an XOR of numbers. It just counts whether the bit string is odd or even. So in the case of UDP checksums, if you take this data structure that's 4 bytes wide and you break it into 2 bytes and 2 bytes and 2 bytes, you know, the different 16 bits mean different things. Some of them are like a number, and some of them are not, there's 3 or 4 different things like flags or whatever, but if you just treat, it's all binary, so if you just treat them like integers and just add them all up and figure out what the least 16 bits are, that's one easy way of doing a checksum. So we'll talk a little bit more about that. So that's kind of what UDP does. It will treat the entire packet as a series of 16-bit numbers, and it will add them all together. And it'll perform what's called a ones complement. So I need to kind of walk you through a little bit about what that means. And then you will stick that result into the packet, and now it becomes part of the data that you transmit. But you're handed the data that does not have a checksum in it yet. You crank it through your formula, you calculate the checksum, you stick it in the spot, and then you send it on. It would be sort of like being given the sticker that shows you can park up front. You know, you pull in, you pay your fee, they put the sticker on the windshield, and now that shows you can park, you know, up front. At the receiving side, you recalculate the checksum based on the data, the fields that they used, and see if you can see an error. All right, so here's an example just adding just two numbers. There may be dozens and dozens of these to add, but let's say these are the only two 16-bit strings in my UDP packet. That's impossible because that's smaller than the minimum packet size allowed. But we'll just show what's going on. So I'm going to add these things up, and hopefully you guys will agree that the addition here is right. 0 and 1 is 1. 1 and 1 carries over. Here's another 1 and 1 that carries over. And so this is my result. Here it gets interesting at the end because I have a 1 here. 1 and 1 is 0. Carry a 1. 1, 1, and the 1 I carried in is a 1, carry a 1. So here's one way, a different way of looking at this math that might make it a little easier for you in figuring out the carryout. That's helped some people a lot. It may not help any of you guys, but let's find out. Okay, so let's look right here. What is 1 plus 0? 1. So far, that's obvious. What is 1 plus 1? No. 1 plus 1. What is 1 plus 1? Thank you. How do you write 2 in binary? 1-0. You're actually going to write this into your number. 1-0. What is 1 plus 1 plus 1? 3. How do you write 3 in binary? 1 and 1. You write 3. Actually write the number. It's always there. It's really there. It's not like this 1 carry 1 nonsense that we've learned all this time. You just add it up and write the actual number down. So if you are adding 25 numbers together and you're all the way over at this last one and there's some carry bits and stuff and you end up with the number 127, how do you write 127 in binary? 1, 1, 1, 1, 1, 1, 1, 1. That's what you write down. You write down exactly that. So you may have to spread it out over columns, but there's no trick. It's just regular math. 1 plus 1 is 2. 2 is 1, 0. Here's the 0. You can write the 1 here if you want. Make it right next to each other. That's fine. It always works. And it's a lot easier sometimes for people, especially if you're adding columns of stuff. Okay, meanwhile, back at the ranch. So I add these things together, and if there's a wraparound, which is basically something that's carried out at the end, then I will drop it back in and add it back in at the end. So what I did was I took this 1 that was part of this 3, that was the 1, 1 here. I took this leading bit and I added it back in here. So I took this whole remaining string here and I added this to it. If this had been several digits long, then I would have written down those several digits here. But adding 1 to this number, as you guys can see here, it's going to change all 3 of these first bits, right? It's going to become 1, 0, 0, which you see here. All right, so that's the sum. So that's the sum I've calculated from all the data that you gave me, which happens to be just two 16-bit numbers. That's the sum. And what do I want to do with the checksum? I could take my packet that I've built, which has room in it for a variety of things. It has room in it for a source and destination port number. And it has a link field. And it has a space for the checksum. And it has data. For UDP, that's all it has. It's a very simple structure. So what I did was I took this whole thing and treated it like a bunch of 16-bit numbers. So I added this and this and this and this and this and this, and then I came over and continued by adding this and this and this and this and this. And I came up with a total, and I did what we showed on the previous slide. I added it up, took any carry out, added it again. Now I have my sum. So where is that going to go? I'm ready to send my packet. I've calculated the very last thing I need before I put it on the network, and there's actually a space in here for a checksum. But wait a minute, I didn't skip over that. Like when I was doing the adding before, I added all of these numbers together. Why is that not a problem? Well, it is there. There's like it's not. But what is the value in the checksum field initially? And does adding 0 change the result of an addition? Never. So it's safe. So now I'm going to stick the checksum in, right? And I'm going to send the packet on its way. So if what I have in here is the sum of all of the rest of the numbers, when I get to the other end, if I repeat the process and add everything back up, what I'm going to end up with is 2 times the sum that I had before. Because adding all the things together except the checksum gives me the sum 1 time. And I put that answer in here, so that's of course the sum the second time. So I will get twice the sum. That's going to be hard to figure out what happened. So is there something that makes more sense to stick in that checksum field than what I had before? Well, one thing you can do is try playing around with complements. 1's complement, 2's complement, 3's complement, etc. So 1's complement is a technique where you simply flip the bits of a string. So what I've done here is I've taken my initial sum and I've inverted the bits. And so what I'm going to do is put the 1's complement of the checksum in here. So what that's going to do is flip all the bits of my sum. So let's see what that does. Why might that be better? Well, let's go find out why. So suppose this is my sum. All right. And now I'm going to send the packet to the other end. If I add all the fields together and I ignore the checksum for a minute, what I hope is that I get the same number back again. So how can I use a 1's complement of the checksum to kind of figure this out? Well, what is a 1's complement? It's a flip of the bits. You just invert the bits. So let's invert the bits. And in that spot in my data where there's a room for the checksum, I'm just going to stick this in here, and I am not going to stick this in here. So what happens now? Well, I know all the other fields in here, except for this one, will still add up to the number they did before if there's no corruption, correct? And what I put in here is the inverse of that. What do I get when I add these together? Well, I didn't invert this one correct. You get all 1's, which is super easy to check. So as my packets come flying in, all my software has to do in binary is add the things as they go by. The checksum is kind of in the middle somewhere, but that's okay. Add it because it's the inverse, and it's all 1's. And at the sender side, this is a really easy change to make to the sum. Just flip the bits. That's easy. I can do that in software easily. In fact, the CPU has an instruction to do that. So when my compiler sees it, it'll go, I know exactly what assembly to write to get that done. So that's why we use 1's complement as a checksum. So the problem with this is that if you change, 1 bit, you'll catch it. But let's suppose what I'm really adding are 5 different numbers. Here's one of them. Here's another one. Third one. And then fourth. And a fifth. Okay. So what I want to do is check to see if there's an error. So let's say somebody comes along and they change this bit. Will I detect it? Yep. You'll add all this up. You add the checksum to it. It's not going to come out all 1's. That's a problem. So I detected it. What if in addition to that error, this was also changed? Will I detect it? Nope, because you're adding up these bits, and they're going to come up with the same total. 1 plus 1 plus 0 is the same as 1 plus 0 plus 0, or 1, 1, 0. You order them however you want to order the bits. I don't think I said it right, but you know what I mean. The order doesn't matter. So that's an error correction scheme that will not work for some types of errors. So why would I pick that? You only want to pick that if you know enough about the types of errors you generally experience to know that this is good enough to catch them. So, bursts of errors, not random spots. Okay, so that's why we use a checksum to get that done. All right, so that's it for UDP. We've talked about that. I'll get us a little bit into TCP, but we're going to spend tons and tons and tons of time on TCP. It is far more important and interesting. UDP basically does nothing. So there's not a lot to learn about it. Okay, so yes. It sure is. Yep, it's in there, and it's in every UDP packet. It's optional whether you implement it or not, but with TCP it is not optional. You must implement it. It does the same type of thing, but there's different rules that have changed over time about whether it's obligatory that you use it or not. And then there are some other interesting things about the fact that maybe it's just the data that's checksummed and not the header as well. Maybe that saves time. And then other layers, that makes them nervous. So we'll talk in more detail about that in a future lecture soon. Right, so that's unreliable. Now what we want to try to design is some way of sending data more reliably. Because most of us send data where we would like to know the whole thing got there, in the right order, not duplicated, et cetera, like emails and files and Dropbox and OS patches and virus download, checkers and all that kind of stuff. We want all of it there. I mean, most of the time that's what you want. Okay, so this is a huge area of research. There's probably been 1,000, I don't know how many, 1,000 PhDs on this area. There's one person who's had more influence on this, I'd say, than anyone else on Earth, a guy named Van Jacobson. And much like Moses showing up from the mountaintop with, what the heck did I just do? Showing up with the stone tablets, Van Jacobson almost literally like showed up at the conference with the answer after like years of trying to figure everything out. He goes like, okay, just let me go away for a while. So he comes back with this paper and just kills it. That's what we use. So after 40 years, he's done it again. He's older, much older, but he teamed up with Google last summer, and they rolled out one of the first big changes to TCP that will be massively used around the world. And his name's right there again. I mean, he's still got it. So he is like the father of a lot of this congestion management. So that's one of the issues that we have to worry about if we're going to want to send something reliably, is how do we avoid congestion so that we know our packets will arrive. So the illusion that we wish to provide is that the network is reliable, when in fact it is not. So the illusion we wish to provide is that to the sending process, they can send us data and it will magically arrive intact as if there was like a pipe or a wire directly from one end to the next. And no chance of anything bad. It's like your own HOV lane on the highway. Wouldn't that be nice? So that's the illusion that we're trying to provide. But in fact, it's unreliable. So what we're going to have to do is come up with some software that will deal with that unreliability. So what we're going to allow the user to call is a function that is reliable data transport send. We're just going to call it that for now. And they hand us data, and they obviously believe that it's going to be reliably delivered because they called reliable data transport, reliable delivery. They'll get your packets there, right? And so on the other side, we're going to deliver the data when it arrives at the other end. So what we have to design now inside this transport layer is all of the extra code that we need to track things sufficiently so that we can guarantee that it is reliable. So this is going to include things like numbering all the packets so we know how to order them, and so we can spot missing ones. We're going to have to develop buffering so that if packets show up out of order and we want to go ahead and hold on to them and wait for the missing one maybe to straggle in, we do that. We're going to have to figure out how long we're willing to wait before we give up on a packet, so we're going to need timers, and we're going to need some ability to resend packets. We're going to need the ability to spot packets that were duplicated, or packets that are corrupted, or packets that came from other people claiming to be someone else and were misdirected. We're going to have to do anything your paranoid mind can think of that could go wrong. If you want TCP to handle it, you're going to have to write the code to deal with it. So there's a whole nother level of communication that's going on between this program and this program, running on two different hosts on two different spots on the internet to kind of create this illusion. Right? So, Garrison Keillor had a interesting quote that I remember once about, people like to say that things used to be simpler when we were young. Nothing was simpler when you were young. Everything was more complicated. Your parents made it seem simpler. Go thank them. So doesn't that make a lot more sense than things were simpler when we were young? So that was his, that was one of his observations. So TCP makes it seem super simple. You don't have to worry about any of this as an application author. You just hand it to TCP and it will deal with all the issues. Retransmissions, rerouting, congestion, the whole 9 yards. So that's what we're going to try to do. And so what this code basically does is it keeps track of the things it needs. Maybe it makes copies of everything, it stores it, it sets timers, and then it will make a call UDT send to really send it over this unreliable network where packets can get eaten at any moment. Okay, so to get a little bit more detailed, RDT send is called from above, so like the application layer is the layer above it. So the application layer is going to do something cause this to get called, and let's suppose this is the name of it. And you will do magic in the middle, and then we'll crank this out at the bottom. And on the receive side, you will receive data, and assuming it passed your test, it's in the right order, it's not duplicated, it's not corrupted, et cetera, you will deliver it up to the waiting companion application. So you two guys are talking in the middle, and the applications above are talking as well. What did I just do? Did I really just close that? Really? How did typing one character go back 4 slides? That doesn't even make a difference. All right, so have you guys ever written finite state machines? We're not going to do it today, but do you guys know what they are? So there's some detail in this book about how to do it, but the last thing I'm going to leave you with is a way that served me well for 30, 40 years of doing this. And you'll find other people have other methods. You can pick whichever one you want. This one works, and it's close to what you need for networking. So you have a variety of states. States are drawn as circles. You will have a name of the state to let you know what is going on. Hungry can be a state, full can be a state, and sleeping can be a state. And to get from one state to the other, you have an event that takes place, and you have a corresponding action that you take. So the event might be, Mom brings food. What is the action you're going to take? You're going to eat, and you're going to say thank you. And in this particular pair of event and action, you are going to transition also from one state to the next. There can be false alarms that cause you to stay at the state. An event can be your stomach growls, and the action you take is, Mom, right? But you remain in that state, correct? To get from the full state to the sleepy state, you let time pass, or Mom tells you it's time to go to bed, and the action you take is hop in bed. And to get from here to here, it might be the alarm goes off, and what you do is get up. Right? That's it. And you have one place where you start, and typically you start with an arrow that just comes in from the clear blue sky. If there's ever an event or an action where there's nothing for you to do, it is traditional to write this symbol, either on the top or the bottom. So if the alarm goes off and you don't do anything, like the phone rings and it doesn't wake you up, there's no action for you to take. So you'll see it like that. Stick with a rule like this. Events and actions always together, separated by a horizontal line. They are always tied to exactly one arrow. So you have as many event action pairs as you have arrows. Arrows go from one place to one place. They can go back to the same location. And you know where to start because you'll have something that looks like something like this. And so that's how you know where to start. So that's the basics of a finite state machine. And we will dive in next time on how can we start building up what we want this unreliable network software solution for this reliable data transport. how can we start writing down the various states that we think things can be in and start deciding like what to do. Like packet timer goes off, resend packet. The state is waiting on acknowledgement, or the state has received a packet from above, you know, something like that. Those are some things that we'll start filling in, and it'll get complicated. Right, so we'll start off. Do you remember in physics class in high school when they taught you the model of the atom? And it was hard, but you worked hard and you got it. And then the next lecture, the teacher came in and said, okay, that was all a big lie. We're going to now teach you another model of the atom. And you're like, ah! Do you remember that? I remember it like it was yesterday, and I'm still pissed after all these years. So we're going to do, I'm just warning you, I'm going to do that to you, okay? So, all right, guys, have a great couple of days. I'll see you online on Wednesday. Okay. Is the WebEx audio